Hello, this is a brief presentation of an air heater control system. The requirements for the system was to use an Arduino to create a PI controller with an analog output to control an air heater, which is regulated with um, a signal from 0 to 5 voltage and which returns a temperature. Um, there was a need for a low pass filter to filter the temperature uh, measurements coming from the air heater to remove potential noise. And the control system should log data, the temperature data, to a cloud server along with its parameters. Then there was desire for physical controls and display in quotations. It's not an actual display, but some sort of HMI or HMI for the controller. Um, this is on the right side here, the controller. Um, and then allow changes for the controller parameters using serial communication. And finally, some digital human-machine interface for monitoring data and monitoring the controller and the changing controller parameters. Okay. The solution that was made is an Arduino Uno R4 Wi-Fi running Arduino and C++ code, um, specifically a C++ PI controller and a C++ low-pass filter with an MCP 4911 DAC unit for converting from digital to analog output. Then, of course, the C++ function for the low-pass filter. ThinkSpeak was used as the cloud server and communicated with the REST API. And then breadboard with buttons and LEDs was used for the physical controls on the controller, which we'll see later. And serial communication was done via the Arduino IDE, which is also where the code for the Arduino is written. And then a LabVIEW program, which communicates with ThinkSpeak, and thus via the controller was chosen for the digital human-machine interface. Here's a system sketch of the controller system. You can see here the air heater, which is supposed to be controlled. Then there is a controller. This is just a controller, which sends a control signal to the air heater and receives back the temperature data, communicates the data in its own settings with the ThinkSpeak, and gets back any updated controller variables if those are changed from the human machine interface, which again receives data and controller variables from ThinkSpeak and gives back controller variables. Yeah. So here first we will take a look at the low pass filter. This low pass filter we can see here. Here we can see low pass filter code, which is in a C++ function. It takes a signal and the last filter signal and some filter constant and dampens the change of the signal. This was tested using two methods. Here first a TNC10 temperature sensor with a resistor, and then a TMP36 sensor, both wired to the Arduino. The signals for them was converted using their own C++ functions. This is the TMP36 here. Simply calculated the temperature from the analog DC signal using a volt reference of 5 and the resolution of 1024. And TNC10 is a little more complicated since it's a scaling one, not a linear sensor. But this is the code. The principle is the same from analog DC power to temperature. Yeah. The results for these were that when the low pass filter was implemented, the temperature measurements became smoother. Didn't become much smoother, but a little. They were quite good sensors. So the TNC did measure quite a lot more realistic temperature than the TMP did. TMP overshot by quite a lot. Yeah. Then you see here ThinkSpeak, the REST API. This is the ThinkSpeak channel right now. It's running. The controller is running, so it's logging data here. This is the temperature data for the test simulator. It has a desired temperature of 24, the controller has. It's using a filter constant of 0.1, KB of 0.8, and TI of 20. Yeah. Then breadboard with buttons we will take a look at now. Here it is. This is the DAC unit, then 2 buttons, 2 LEDs with their own resistors, all wired to the Arduino Uno, and then this is voltage to the air heater, and this is the grounding of the air heater. Yeah, I don't have the air heater right now, so I'm using a digital simulator, which I have coded myself. This is the air heater simulator right here. Just a simple mathematical model, only it has 0 delay. The actual air heater does have some delay, but it's fairly representative. Okay. Yeah. Back to here. Serial communication with the Arduino IDE. This is the Arduino IDE. This is the code for the running on the Arduino right now. Here's the main loop. It calculates the controller and signal and sends it to the air heater simulator and receives back a temperature which is filtered. Then it prints data here, which we can see underneath here, and then it determines whether it should update ThinkSpeak or not, and it tries to read ThinkSpeak data if it's changed, and then all the different functions are underneath here. Yeah. So right here it prints data. This first one here is minutes since it updated ThinkSpeak. The second one here is the control voltage it's using. This is the reference temperature, and this is the actual temperature of the simulator. You can see that when it reached 1 minute, it updated the ThinkSpeak channel. And now that it has stabilized in temperature, the voltage signal is dropping. Yeah. We can also see in this, set up a camera here, which shows the output to this multimeter is acting as the air heater right now. We can see here that it changes the signal. It doesn't quite reach up to 5, but close. Then LabVIEW communication. This is the controller right now. Here we can see that it has reached 24 degrees, which is what it's showing here, and that it has gotten the correct values for the controller from ThinkSpeak. Yeah. That is the controller. So security-wise, data is uploaded using an API to the ThinkSpeak. So we need, as ThinkSpeak handles this, we need an API key, which is hard-coded into the compiled controller, the digital and the digital human-machine interface LabVIEW program. And of course, you cannot extract these codes after they've been compiled, and you cannot extract the code back from the Arduino after it's been uploaded to it, which makes it impossible to acquire the API key. For future improvements, there is some problems with how often it logs to ThinkSpeak, because there's a limit in ThinkSpeak of how often you can update the channels. It's 15 seconds, which for this controller is not as fast as I would have liked if it was to be representative shown in this video. But that's how it is. And if I had actually bought ThinkSpeak, I could have updated it more often, and this problem would have been solved. We can also see the physical controller live here on this camera. Here in the end, this is the controller here. We can see that there is green and a yellow LED down there, and 2 buttons for raising and lowering the desired temperature. So this has been a control system summary that I have presented. It's a working system that logs to the cloud and has a digital and a physical human-machine interface. But it could have been improved. Thank you.